This video is on batch normalization. In addition to covering batch norm, as well as understanding the entire batch norm paper, we would also look over three other papers, which try to make sense of the unreasonable effectiveness of batch norm. For most of the deep network that you would work with, especially CNNs trained on vision tasks, batch norm would be present between the layers to enable stable training and faster convergence. But before jumping into what these batch norm layers are, let's look at a much earlier part of the network, our inputs. A common technique for training our neural network is to take our input features and transform them. This transformation typically involves standardizing the features by subtracting the mean value of that particular feature over our dataset, as well as dividing by standard deviation. Other kinds of transformations are also used, but for now, assume standardization is what we have. This essentially makes each of the features to have zero mean and unit variance. There are quite a few good reasons to do this transformation. Assume our output is this linear combination of two features, and our goal is to learn the weights W1 and W2. When we have features that are of very different scales, contour plots of the loss function would have the shape of an elongated ellipse, where the gradient does not always point to the minima. Small change in weights corresponding to larger scale features will obviously lead to larger changes in the output. If we use a higher learning rate, then either the loss will completely diverge or the loss will just oscillate. Only when we lower the learning rate to a much smaller value, we will have chances of convergence. But then because of this lower learning rate, training is going to take a lot of time. When we use this zero mean and unit variance transformation of features, the chances are more that we get symmetrical curves, where gradient usually points to minima, and this allows better convergence. The zero mean is also beneficial when we look at how the change in weights affects the output and weight update equations. If our features are all positive, then all the weight updates would always end up to be in the same direction, which means the update during gradient descent will either increase both W1 and W2 or decrease both of them. But maybe the most optimal direction of change is increasing W1 and decreasing W2. So having positive and negative xi's would be nice. Normalizing features would also be beneficial even if all the features were at similar scales to begin with. Activation functions like sigmoid, which bake in non-linearity in our model, will benefit if the feature values are in a nice range. This zero centering and unit variance transformation seems to be very nice for better training of our models. From the inputs, let's move to the intermediate layers. For any layer, the inputs are going to be the outputs of the previous layer. So if the transformation of features at the input layer of network benefits us, ensuring that the inputs to each intermediate layer also has zero mean and unit variance could also be beneficial for smoother training. After all, each layer is itself a subnetwork working on the outputs of previous layer. This is the main aspect of batch norm, that we do scaling and zero centering for inputs to intermediate layers as well. The authors of batch norm mention something called internal covariate shift. When we later look at results, we see that batch norm speeds up convergence and leads to efficient training. The authors claim the effectiveness of batch norm is because it reduces this internal covariate shift. Picture this. We have a neural network, and in the first forward pass, based on some initialization of weights, this layer sees a particular distribution of input values, which are nothing but the output of previous layers. Based on the loss, when we do a backward pass, the parameters of previous layers would change. But this change of parameters would also cause a change in the distribution of values that this layer with blue nodes receives as input. So the network would have to continuously adapt to this changing distribution of each layer's inputs. And with deeper and deeper layers, small changes in parameters of all previous layers would amplify to cause large changes in distribution of inputs to later layers. The change in distribution of input data or covariates from training time to test time negatively impacts the performance of our network. So just like it's beneficial to not have this shift in the inputs of the network, thinking of each layer of our deep neural net as a subnetwork, the authors claim that fixing the distribution of inputs for each layer or the outputs of the previous layer should also be beneficial. This change in distribution of layer inputs during training is termed as internal covariate shift, and the authors seek to reduce this for better training. The approach they use to ensure this internal covariate shift does not happen is similar to how we transform and standardize input features to have zero mean and unit variance. How exactly does this transformation take place? Assume we are working with d-dimensional features x1 to xd at a particular layer. Each feature is independently transformed by subtracting the mean and scaling down by square root of variance. In implementation, we also add a very small value to the variance for numerical stability. Ideally, to standardize the values of a particular layer, we would compute the mean of this feature over our entire dataset. So we take all the d data points, forward pass it to the network with the current weights, compute the mean using values obtained for that particular layer's feature, and similarly compute the variance. But this will introduce a lot of computation overhead. As for each forward pass, we would have to go over the entire dataset. So instead, the authors use statistics computed for the batch as an estimate of the dataset statistics. Each data point generates the d-dimensional feature values for a layer. Assuming a batch size of m, we will have m such d-dimensional features for this layer. Then for computing the mean of the 0th feature of a layer, we get the m values of the 0th feature from all data points in the batch. And repeat the same for all d dimensions to get d mean values for the entire batch for this layer. Similarly, we get the variance values and standardize to get the transformed d-dimensional feature for this layer. This transformation happens in every forward pass during training for all layers which have batch norm. What we talked about captures fully connected layers. Let's also see how the mean and variances are computed for convolutional feature maps. Each channel of a convolutional feature map would be a feature, and BatchNorm would standardize each of those features over the entire batch. So we have a C cross H cross W feature map, and assuming batch size of m, we will have m such feature maps. Since the filter weights of a conv layer are shared across the spatial dimension of the image, the authors standardize values at different spatial locations of the same feature map in the same manner. For conv layers, the mean values are computed by averaging over not just the batch, but also all spatial locations of channel. So for transforming features of the first channel, we use these values to compute batch stats. For second, these. And for the last channel, which is the third channel in this example, these values are used to compute mean and variances. Once these batch statistics are computed, we transform the feature in the same way, standardizing using the mean and variance. Throughout the video, we have been talking about transforming activations, but the authors of BatchNorm actually transform pre-activations. Assuming these are the activation values of layer I. These are the weights to compute the first pre-activation value of the next layer j, and these to compute the second value. We would also have some activation function to compute activation values for layer j. The authors place the batch norm layer prior to the activation function, after the W transpose X computation is done. They reason that the pre-activation values computed using W transpose X would be more Gaussian, unlike the distribution of values obtained after non-linearity. So constraining the moments of the W transpose X distribution is more likely to eliminate covariate shift. Furthermore, standardizing pre-activation values also means that your activation function, at least non-ReLU activation function, gets a nice range of values as input, so nice gradients. Most of the networks using BatchNorm indeed place it before activation, but placing BatchNorm after activation also has been shown to work, as done by experiments on this repo. And if you think from a subnetwork perspective, standardizing activations would mean that the inputs to the next layer are zero-centered and have unit variance, which, as we saw earlier, should be a good thing. Also, papers that we will look at later have shown that the whole notion of batch norm reducing internal covariate shift might not be the reason of its success after all. If that's the case, then the reasoning given by the authors that placing BN before activation leads to higher chances of stable distribution, this might not be a good enough reason anyway. Whether to place it before or after activation function is something one can always experiment with based on the model and dataset. However, most networks have batch norm prior to the non-linearity. For the rest of this video, that is what we'll assume, which means these xi values are the pre-activation values computed at each layer. Within the batch norm layers, the authors also introduce couple of parameters, which if needed, can convert the batch normalization transformation to be identity transformation. Standardizing the pre-activations would lead to modifying the representational power of the network, potentially even making it weaker. Like for sigmoid activation, since the pre-activation values are zero mean and unit variance, that means we have essentially reduced it to linear region. But that might not be the optimal thing to do. So once we have standardized the values, we transform the distribution using two learned parameters for each transformed value of our layer. One of them is scale and the other is shift. So if retaining the original distribution of values was the optimal thing to do, then the network could learn the scale parameter to be of value closer to the square root of variance and shift to be closer to mean, making the final transformed value same as the original value xi. Again, if that is what the network believes is the most optimal thing to do. Otherwise, these parameters just modify the distribution to be non-zero mean and variance of some value other than 1 based on what their values are. During training, the scale value is initialized as 1 and shift as 0. And from there on, the network can transform the distributions as it deems fit. These scale and shift parameters are interesting, given the core reasoning of batch norm being internal covariate shift. Since as the network is trained, these scale and shift parameters would also change, which means the distribution of these activations would also keep changing. Although I'm guessing the change in consecutive steps would be less drastic than in the case without batch norm, at least for later layers, but still the shift would indeed be there. Here is what we have in a batch norm layer up till now. We compute batch mean and variance, we standardize the pre-activation values, and then scale and shift them using our learned gamma and beta parameters. This is actually the entire logic for batch normalization during training. We will look at inference also, which has few changes, but before moving to inference, let's look at how the gradients with respect to all parameters involved are computed. This is just for completeness sake. The deep learning framework would anyway take care of it, but since it's mentioned in the paper, let's see it once. To make more sense of these equations, it's better to start with how the variables involved and their dependencies look like from a computational graph standpoint. We have all our pre-activation values computed by the network for a particular layer and particular feature for the entire batch, giving us as many values as the batch size. All these are used to compute the mean. The mean and individual feature values are then used to compute the variance. These original xi values are then standardized using the computed batch statistics. Using the scale and shift parameters, which will be different for each feature, we compute final values for the entire batch, and that will be fed to the activation function. Now let's look back at the gradients. We won't be computing these values, but just leave at understanding the reason behind different terms in each gradient. For the gradient of scale parameter, the relevant parts are these nodes. Since this parameter is used for computing transformed values for the entire batch, we will need to sum over gradients from each batch item. The scale and shift equation can then be used to compute the exact expression for the gradient. For shift, the same thing holds. For each batch item's standardized xi, we are now concerned with this part. So based on our scale and shift transformation, gradient would be dl by dyi times scale parameter. Now we are moving to gradients of mean and variance. For both, focusing on these set of nodes is enough. Both mean and variance are used to standardize each batch item xi, so we have to again sum over gradients from each batch item. For variance, the standardization equation and variance expression will give us our gradient. Similar approach we need to follow for mean. However, since computing variance also requires the mean, apart from summing gradients from each batch item, we also have to take account of how the variance changes with respect to mean, which is this second term. The gradient for original pre-activation values xi are captured by these set of nodes. Xi's are used to compute mean, variance, as well as transformed xi hat values, which means the gradient for xi will have terms involving all three, and how those change with change in xi. Now let's focus on the inference logic for batch normalization. The notion of using batch statistics to get an estimate for mean and variance allows us to implement the training part of BatchNorm. But using batch statistics for inference might not be a good idea. During inference, we don't want the output to change based on what other data points are being inferred in the batch. As of now, depending on other data points, the statistics will change, causing the output to also change during inference. But we wish the network output for each data point to only depend on each input deterministically. To get around this, during training, the authors use moving average to keep a track of the running estimate of the mean and variance for each feature. In implementation, this means we add these two lines of code, where running mean is initialized to be 0 and running variance is initialized to be 1. Beta is a hyperparameter that decides weight that is placed on values seen in the past. In practice, a high value like 0.9 or 0.99 is used, which means larger weight is placed on values that we have seen in past, and lower weight is placed on values that we are seeing now in the current batch. For a large number of steps, the running stats should get closer to the population statistics. Then once our training is done, for standardization of each value during inference, we use these running estimates rather than batch statistics. That way, removing the dependency on other batch items. After we have our transformed values based on the saved running stats, we then have the same scale and shift using our learned parameters. To demonstrate the benefits of BatchNorm, the authors first train a very simple network with just 3 hidden FC layers on MNIST dataset. Adding BatchNorm to this network results in a much more efficient training and quicker convergence. The authors also use one of the activations from the network to demonstrate that without BatchNorm, the distribution of activations change a lot, especially in early stages of training, whereas with BatchNorm, it's more stable. Using the inception architecture and training on ImageNet dataset, the authors show that with BatchNorm, we can use higher learning rate without the model diverging during training. This allows us to train the model faster and even reach higher accuracy. Moreover, because of BatchNorm, we can even train this model with sigmoid as the activation function. Without batch normalization, the same model wouldn't be trainable. This large learning rate, which allows quicker convergence, is possible because 1. BatchNorm prevents activations from exploding by keeping them in a nice range, and 2. Because even with large learning rate, increasing scale of parameters, the gradients won't increase. The authors show this for input U and weight W, which then goes through a batch norm layer. So in the illustration that we were working with earlier, the xi's are computed by multiplying U with weights W. Even if the scale of weights change to A times what it was before, the gradients do not undergo an increase. In fact, for the parameters, the larger scale leads to smaller gradients, ensuring that even with higher learning rate, training remains stable with batch norm. One can see why this is the case using the gradients expression from earlier in the video. When the scale of values increase, so will their mean and variance, and once you plug that scale factor in those expressions, you will see that increasing scale of parameters does not amplify the gradients. In BatchNorm paper, the authors also mention the benefit of regularization with BatchNorm. Assume we have these training data points in our batch. Let's focus on computing batch normalized values for activations for all layers on this one. The output of batch norm layer would change based on other data points in the batch. During a different training step, rather than these batch items, the same image of 1 could be present with these different images, leading to a different mean and different variance, which means the network output would produce slightly different values for the same input. The authors compare this to dropout, where we randomly drop activations by multiplying them by 0. Here in batch norm, this mean and variance will fluctuate because different examples are randomly included in our batch, which means they can be treated as injecting random noise to the pre-activation values. We are multiplying by a number that will fluctuate, and we are also adding a number which will also fluctuate. Both of these sources of noise add a form of randomness to the behavior of network on this sample image of 1. This should encourage layers of the network to be more robust to slight variations in its input, in its attempt to be robust to these fluctuations, which in turn should improve generalization of our network. The authors indeed found that with batch norm, dropout in networks can either be removed or reduced in strength. This small addition of standardizing values in a layer brought about significant benefits in terms of training speed and accuracy, but there are also few problems. Small batch sizes will make the batch statistics very noisy. So with batch norm, it's better to use larger batch sizes. But that might not always be feasible like in object detection or segmentation tasks. With batch norm, we have a network that behaves differently during training and inference. The running estimations could introduce a discrepancy between model performance during training versus testing. We have also added some extra computations in our model, but obviously in return we get better performance, so that's a trade-off that we are mostly fine with. There are other normalization techniques which do not have some of these specific problems, and in future videos I'll try to cover those as well. The last section of this video will go into some of the papers which try to reason on why batch norm is so effective. Though the original paper gives reduction of internal covariate shift as the reason of batch norm's success, but some of the later papers show that the effectiveness of batch norm does not necessarily stem from this reduction of distribution shift. I will briefly talk about these three papers, and the goal will just be to get an overview of them rather than covering them in depth. The first one is understanding batch norm. The authors of this paper credit the higher learning rate that BN enables to be responsible for majority of batch norm benefits. A ResNet model without batch norm trained on CFAR 10 requires the learning rate to be reduced to 1e-4 for convergence. The authors find that when the same learning rate is used for training ResNet with batch norm, it performs no better than the unnormalized network. It's only when the learning rates are increased, the convergence and accuracy gap because of batch norm emerges. In their experiments, they found that the higher learning rate is not possible for unnormalized network because it diverges for large learning rate, typically in the first few mini batches itself. So they plot the relative change in loss, that is new loss divided by old loss, with respect to step size, and identify when a network update leads to a change in loss greater than 10 to the power 3. as from this situation, their network never recovers in experiments. Obviously, for BatchNorm network, this divergent update will happen at a much larger learning rate, whereas for the unnormalized one, it will happen even for a relatively small learning rate. But what's interesting is the mean and variances of activations in the network at the time of a diverging update. As we go deeper in the network, the scale of activation grows progressively larger, hinting that the divergence is caused by this explosion of activations, which BN successfully would have avoided. This progressive growth of activations is even true right at initialization. Looking at gradients at initialization for a middle layer, we can see the difference in gradient magnitude with and without batch norm. And when we plot the mean and variances, it's clear that for unnormalized network, the activations grow exponentially. And again, this is at initialization. The authors believe that this huge difference between input and output at initialization itself is what is causing the large gradients. To test this, they train a ResNet with only one batch norm layer that standardizes output of last residual block, and just that. This small change in architecture increases the feasible learning rate of an unnormalized network to 0.03 and gives a test accuracy of 90.1, much closer to a batch normalized network than an unnormalized one, indicating that standardizing output of last layer could potentially be the most important difference between batch normalized and unnormalized network. The paper goes into a bunch of other experiments as well, but here we are just doing a quick overview, so I won't be getting into those. Let's move to the second paper, which is how does batch normalization help optimization? The authors of this paper perform a lot of experiments to understand the cause of batch norm success. They conclude that unlike what the BN authors say, internal covariate shift reduction and distributional stability of layer inputs does not impact batch norm effectiveness. Rather, batch norm impacts the optimization landscape, making it much smoother, which ensures that gradients are more stable, and that is what causes faster training and better convergence. To start with, in order to validate the claim that constantly changing input distribution for layers is a problem that BatchNorm solves, the authors of this paper sample activations of a given layer and visualize how the distribution changes over training steps. The difference as far as stability of distributions between BN and unnormalized network is not that significant, even though the performance difference is. Furthermore, the authors implement a noisy version of BatchNorm. In noisy BatchNorm, at every time step after each value is batch normalized, we perturb it for each sample in a batch, with noise sampled from a non-zero mean and non-unit variance distribution. This distribution itself varies between steps. So for every pre-activation value in the batch, at every training step, a different noise will be added, making the input distributions at any layer changing with time. If internal covariate shift indeed leads to ineffective training, the performance of noisy batch norm should take a significant hit. But that is not the case. Its performance is much better than unnormalized network and almost same as standard batch norm network. This means that the internal covariate shift, at least as measured by the mean and variances of input distribution, is not really influencing training. But what if we define internal covariate shift from an optimization perspective? The authors start looking at ICS or internal covariate shift as how much the parameters in a layer would have to adjust in response to a parameter update in the previous layers. To quantify this, the authors use difference between the gradients of each layer before and after updates to all the previous layers. So let's say we have this neural net, and this layer is what we are observing. Using the loss and current parameters, we'll get the gradients for this layer. Then based on the computed gradient, update all layers prior to the one that we are observing. So the layers later in the network are fixed. And now using the same input and output, compute gradient for this layer again. The authors run experiments to identify if batch norm reduces this notion of covariate shift. which means is the gradient difference significantly lesser in batch normalized network than in an unnormalized one? If that is indeed the case, then we can say that batch normalized network layers will have to do less work to adjust to the distributional change from updating all prior layers. However, batch normalization doesn't offer any advantage from this perspective as well. The gradient change, be it in terms of direction or magnitude, is not lesser than unnormalized network. The authors claim that based on these experiments, internal covariate shift and its reduction has little impact, which means the effectiveness of batch norm must be from some other reason. In the paper, they show that batch norm's effectiveness is actually because it makes the loss landscape significantly smoother. So the landscape, which earlier had large number of kinks, sharp minima and flat regions, that landscape now becomes significantly smoother. To show this, the authors compute gradient at a particular step based on the current parameters of the network and then take steps of different sizes in that direction, say alpha, 2 alpha, 3 alpha, and so on, where alpha is the learning rate. Then they take note of gradient and loss after updating the network with these different step sizes. At each of those step sizes, they measure how the loss and gradient changes. If the gradients are very different at each of those points, that means the gradients of the loss are not smooth and unpredictable. Whereas if the gradients at each of those points tend to be similar to each other, that means the loss landscape is much better for optimization than before. These plots are just to illustrate that if the gradients are predictable and smooth, then we have a better optimization problem. Comparing batch normalized to unnormalized network, the change in loss as well as gradient is significantly larger for non-BN network. The first plot is the difference between minimum and maximum loss found within the set of different step sizes that they take. The second one is the same but with gradient magnitude. And the third one captures the ratio of maximum change in gradient over distance moved. One can see that batch norm reduces the gradient and loss magnitude difference between those step sizes, meaning that batch norm makes the landscape smoother and ensures that gradients are more predictable, leading to a better optimization problem for the model. In paper, the authors also give a theoretical perspective to this, showing why batch norm makes this loss landscape smoother and ensures why the loss does not change too quickly between two neighboring points. They further show that the same impact can also be achieved if we scale activations using other normalization strategies like L1, L2, and so on, instead of scaling activations using variance. To do this, they fix the first order moment of activations, but then normalize them by the average of their norm prior to shifting the mean. The same benefits that we see with batch norm, we also see with these cases. Change in gradient and loss is much smoother, and they also get similar performance as batch norm. This means that fixing the distribution of activations, like batch norm attempts to do, is not why batch norm is effective, because these other normalization strategies do not ensure distributional stability. Let's move to the last paper that we will discuss in this video, which is more focused on the effectiveness of batch norm on residual networks. A residual network has residual blocks. Each block will take the input and usually pass it through a conv batch norm ReLU layer. In reality, there would be a stack of these layers. Then the output of these layers, as well as the input, is added together, and that becomes the input of the next residual block. A typical residual network will then have a large number of these residual blocks. Focusing on one of these blocks, and for simplicity, let's go with only one layer. The input to this layer will be XL, where L represents the residual block number. Then the output would be XL plus 1, which will be XL plus FL of XL, where FL represents the function computed by the residual branch of the Lth residual block. Since batch norm will normalize the pre-activations to have variance of 1 and scale and shift parameters are initialized as 1 and 0, so using this, the authors show that the variance of the input to L plus 1th residual block would be the variance of input to lth residual block plus 1, which means the variance of input increases linearly as we go deeper in the residual network. Comparing this to an unnormalized residual network, having conv ReLU rather than conv BN ReLU, the authors show that without batch normalization, the variance of the input to the lth residual block grows exponentially. Since batch norm will return output with variance 1, it means it will suppress the hidden activations of the lth residual block by square root of L. This is because the input to the lth residual block will have variance L, which would cause the BN layer to divide by square root of L. So the residual branch contributes a smaller fraction of variance to the output of residual block as compared to the skip connection branch. As we go deeper and deeper, so L keeps on increasing, this causes the output of lth residual block to be more and more dominated by the skip connection. This ensures that early in the training, the function computed by batch normalized residual blocks are closer and closer to identity function as we go deeper and deeper. It's this impact of batch norm that preserves signal propagation in both forward and backward pass, as well as better gradients, ultimately ensuring more effective training with batch normalized residual networks. Based on this, the authors attempt to train an unnormalized residual network by simply downscaling the residual branch using a learnable factor alpha. They find that as long as alpha is initialized at a value of 1 by square root of d, where d is the depth of residual block, training is feasible. But they recommend alpha to be initialized as 0, so that the residual block represents identity at initialization. With batch norm, training ResNet with large number of residual blocks is obviously feasible. And we know without batch norm, training diverges. But in unnormalized network, if we downscale the residual block with learnable factor alpha, and the authors call this network skip init, then we are able to train 1000-layer ResNet without batch normalization. However, this is only feasible if we initialize alpha with a value smaller than 1 by square root of d. If we initialize with a higher value, we still end up with the same problem. These experiments are meant to support the claim made by the authors that batch normalization enables us to train deep residual networks by biasing residual blocks towards the skip path at initialization. The authors also do experiments regarding batch size and regularization, but we are not going to cover those in this video. So please give this paper a read if you are interested. While I did try to cover the most important aspects of batch normalization, as well as some papers that I found very relevant, it's best if you read them yourself because for the sake of time, I left quite a few aspects from some of the papers. I also suggest going over the batch norm implementation in the deep learning framework that you are comfortable with.